All right, one thing I want to talk about before I move on that came up in class today was when you have multiple springs. So there was a test question on the last test where they had some springs that are called in parallel. So they're in parallel when they are parallel to each other and added together. And then they wanted you to compare it to two springs that were in series. So in series means that they're connected to each other. So I have this spring with a spring constant and then the second spring with its spring constant in each of these situations. And then it wanted to know the total spring constant. So in parallel is easy. You just add them together. So if you had two springs, you would just add them together. If you had a third spring, add that one in there. So for example, if these are each 4 newtons per meter, then the total spring constant is just the 4 plus the 4, or 8 newtons each meter. In series, it's a little bit different. You have to take the inverses. So you have to add the inverses, then take the inverse again at the end. So for our example, if we do the same thing with 4 newtons for each meter for our spring constants, then it would be 1 over 4 plus 1 over 4, which gives me 2 over 4. But then we have to take the inverse, so my total spring constant would be 2 newtons each meter. So basically what you get is if they're in parallel and they have equal spring constants, the spring constant for the whole thing is double. If you have 2 springs, it would be triple if you had 3 springs. If they're in series, it's actually cut in half. So the more springs you add in series, the smaller your total spring constant will get. All right, now let's talk about pendulums. So let's talk about the simple pendulum first. All right, so a simple pendulum is just how it sounds. You have a string with length L, and you have a mass on the end of your pendulum, okay? And you release it for some height. I do not like the way that line came out. Release it from some height, and it's going to swing back and forth here. The restoring force for a pendulum is the gravitational force. Okay, but it's not the straight up and down gravitational force. It's a component of the gravitational force. So the gravitational force would be straight down, but the gravitational force is pulling it back here to equilibrium, which is this point. But then it's going to offshoot and go to the other side. The component of that gravitational force is going to change direction. Well, that gravitational force is mg sine theta. Ooh. That's your restoring force for the pendulum, okay? So now we can look at the angular acceleration. So this also travels on a curved path. So we get the torque in there. The restoring force is in the opposite direction of that displacement or angle we put it at. This is a cross product. So this is the other way you can figure out that it is mg sine theta. That's what you get for the cross product. The radius is just the length of the string. So you get mg, L is the length of the string times that mg sine theta for your restoring force there. Okay, so then you get your angular acceleration. I'm just taking it from rearranging this equation. Is the negative L mg sine theta divided by that rotational inertia of the pendulum. Well, the rotational inertia for this, it's a point mass, It's going to be ML squared because it's just going to be the length of the string. Again, that's your distance from your pivot. Oops, I hate when that happens. So what I get is alpha is equal to negative L mg sine theta over ML squared, or negative G over L sine theta. Okay, that's your angular acceleration. All right. For small angles, the sine of theta is roughly just equal to theta. This is for small angles. Okay, so that means that the second derivative of theta, which remember is angular acceleration, plus G over L theta is going to equal 0. This is your second derivative of the angular, angular displacement. Okay, this is only true in simple harmonic motion. So now I can look at angular velocity or angular frequency, which is going to be the square root of G over L. Okay, that's coming from this acceleration and the angular frequency we talked about with springs. Okay, we also said that angular frequency was 2 pi over t, which is period, or the period was equal to 2 pi over the angular frequency. So I can now rewrite this as the period is 2 pi over the square root of G over L, or taking that inverse, I don't know what I was writing there. It is 2 pi square root of L over G. So the only thing that affects the period of a simple pendulum is the length of the string and the gravitational field strength. Okay, for springs, the only things that affect the period are the mass that's attached to the spring and the spring constant. All right, so that's where the period of the pendulum equation comes from. There are two other types of pendulums, a torsion pendulum and a torsion pendulum would be if you had some sort of like rotating disc here. I can not draw to save my life. Give me a second. That's a little better, but not great. But basically what you're going to have happening with this disc is a twisting motion back and forth. Okay, well, the torque that's being applied to this is equal to K times omega, or this now is not a spring constant, but a kappa, which is a torsion constant, okay? You don't necessarily need to know all of that other than this has shown up on multiple choice questions. So I'm showing you where the period comes from here. And so the period for a torsion pendulum is dependent on the square root of kappa, or the torsion constant. Oops, not in the top though. The rotational inertia of that torsional pendulum, which would be a disc in this case, so it'd be the rotational inertia of a disc divided by the torsion constant, or that kappa. Okay, again, torsion pendulums do not show up very often. I've only seen them in multiple choice maybe once or twice. But one that does show up sometimes is the physical pendulum. So a physical pendulum would be like an oscillating meter stick. Okay, so if I pull the meter stick over to the side and then allow it to rotate back and forth, that would be a physical pendulum. Okay, a kid swinging from the monkey bars back and forth would be like a physical pendulum. So the period for a physical pendulum is dependent on the square root of the rotational inertia of that object plus its gravitational force plus this h, which is the distance from the pivot to the center of mass. Oops. Well, the center of mass doesn't have to be in the center. That's the center of mass. So h is the distance from the pivot to the center of mass. So this is basically if you have a solid object rotating back and forth or oscillating back and forth, it would be a physical pendulum, okay? It's not all of the mass concentrated at one end. This is if I have mass throughout the whole object, okay? Again, doesn't come up super often, but it does come up sometimes, especially in multiple choice. All right, I hope this helps at least a little bit. If there's anything I can help you with, please let me know. I'd be more than happy to help you out. Have a great day.